Okay, now here's our first example. So we've got example 1. Okay, so example 1. Okay, show that if A, B, C and D are positive, then A to the power of 4 plus B to the power of 4 plus C to the power of 4 plus D to the power of 4 is greater than or equal to 4 times A, B, C, D. That's part A. Then you'll have to prove B, C and D. Now let's start off with part A. So here are our solutions. Okay, part A. Now we can recognise this as similar to A squared plus B squared is greater than or equal to 2AB. So let's just prove that first, and then we can do similar things with the B and C and the C and D, and then we'll just see what we come up with. Okay, so let's just start with, we're going to start by proving. So first we're going to prove that A squared plus B squared is greater than or equal to 2AB. So to start to do that proof, we go A minus B squared is greater than or equal to 0. So A squared minus 2AB plus B squared is greater than or equal to 0. Therefore, A squared plus B squared is greater than or equal to 2AB. Now, notice we don't have A squared and B squared, but this really is the square, the sum of the squares of two numbers is greater than or equal to 2 times the product of the numbers. So here, if we replace an A with an A squared, and we replace B with a B squared in this expression, therefore we can say that A to the power of 4 plus B to the power of 4 is greater than or equal to 2 times A squared times B squared. So using this result here and replacing A with A squared and replacing B with B squared, we will end up with A to the power of 4 plus B to the power of 4 is greater than or equal to 2 times A squared times B squared. Okay, now I'll call this one equation 1. I'll call this equation 2. So make sure that you label your equations when you're doing this. Now we can say, well, similarly, if we replace in this expression up here, we can do a relationship between B and C, or we can do a relationship with C and D. Okay. So looking here, we've got our A to the power of 4 and our B to the power of 4. We'll still need our C to the power of 4 and our D to the power of 4. Of course, any of these could be, I could replace A with A squared, B with B squared. I could replace the A with C squared, or the B with D squared, etc., etc. So I can just write here that similarly, just using this, I've got C to the power of 4 plus D to the power of 4 is greater than or equal to 2 times C squared times D squared, and I'll call that equation 3. Now, here we're going to add equations 2 and 3 together because they are inequalities in the same direction. Okay, so we've got adding inequalities 2 and 3. Okay, we've got that A to the 4 plus B to the 4. Sorry, I'm just running off the screen. Okay, so adding inequalities 2 and 3, A to the power of 4 plus B to the power of 4 plus C to the power of 4 plus D to the power of 4 is greater than or equal to 2A squared B squared plus 2 times C squared D squared. Now, we're getting there. We have to make this into 4A, B, C, D. So we've got 2 as a common factor here. So therefore that's greater than or equal to 2 A squared B squared plus C squared D squared. So 2 lots of A squared B squared plus C squared D squared. Now, just stopping there for a sec. I better just move this down as well because you can't see it properly. Now, using this here, I'm just going to come over the side here. You know how we've got A squared B squared plus C squared D squared? Well, we can really say that that's AB squared plus CD squared. Now, we know our original inequality that A squared plus B squared is greater than or equal to 2AB. So I can say, well, that is greater than or equal to, just using this over here, I just need a bit of room over here, that's greater than or equal to 2 times that times that. So therefore, this expression, this bit just here, A squared b squared plus c squared d squared, well, that's greater than or equal to 2 times a, b, c, d. So therefore this is greater than or equal to 2 times 2a, b, c, d. I'll just put that there, 2a, b, c, d. So therefore it's greater than or equal to 4a, b, c, d. Okay? Actually, I should just write that expression out every time, but I've just run out of room there. Okay? Actually, what I can do here, I can put that, wait a sec, this expression there equals this one, but then this is greater than or equal to that one, and that happens to equal this one. Okay, so there's equality from this row to this row, but then this is greater than or equal to that using, see here, we're using the result that a squared plus b squared is greater than or equal to 2ab. That's what we've done when we've written this, okay? So therefore we can write the conclusion that a to the power of 4 plus b 4 plus c 4 plus d 4 is greater than or equal to 4ab cd. Okay, that's part A. In part B of the question, we have to prove that a squared plus b squared plus c squared is greater than or equal to ab plus bc plus ca. Now what we're going to do is we're going to use bits from part A of the question. All right, let's just start with a squared plus b squared plus c squared is greater than or equal to, we're trying to prove that. Now we do know that a squared plus b squared is greater than or equal to 2ab. Now we use that in part A of the question, and we use that inequality. Similarly, we can say, similarly, we can say, well, I'll call this equation 1, okay? Similarly, we can say that b squared plus c squared is greater than or equal to 2bc. Okay, I'll call that one equation 2. And again, similarly, we can say that a squared plus c squared is greater than or equal to 2ac. Now, in question A, we didn't do any of this repeating. Like, we didn't really need to, because we had a4 plus b4 and then we had c4 plus b4, d4. We did have 4 terms in part A, so we didn't really need doubling up there. But in part B, we've got 3 terms, so you are going to need to double up on everything. Like, you can't do a squared plus b squared and then just b squared plus c squared, because the b squared's doubled, so you need to double up on the a squared plus c squared as well. So we've got equations 1, 2 and 3. Here, if we add equations 1 and 2 and 3, we're going to get 2a squared plus 2b squared plus 2c squared is greater than or equal to 2ab plus 2bc plus 2ac. And just coming over here, sorry, just run out of room there. We can now just divide through by 2. Actually, I can probably just do it here. So if I now divide through everything by 2, I will get, now the reason we could add these 3 together is that the inequalities were all the same way. So we added the 3. So dividing through by 2, sorry. Okay, as I said, dividing through by 2, we get a squared plus b squared plus c squared is greater than or equal to, dividing that by 2, we get ab plus bc plus ac. And therefore that result is proven. Okay, now for part C of the question. Question is, deduce that if a plus b plus c equals 1, then ab plus bc plus ca is less than or equal to 1/3. To start this off, we're going to start with the result that a plus b plus c squared. Now we're doing it like this because we know that a plus b plus c is 1. So we're starting off with a plus b plus c squared. We know that that is equal to a squared plus b squared plus c squared minus plus 2 lots of AB plus BC plus AC. Remember, we looked at that in the previous video as just one of the things that would be very useful. It's a very useful relationship that you can use. Again, the reason that we're using it is that we know A plus B plus C is 1. Also, I think in part B, we looked at a relationship. In part B, we looked at the relationship between A squared plus B squared and C squared. And we knew that it was greater than or equal to AB plus BC plus AC. So I'll just write down what you had in part B. In part B, we proved that A squared plus B squared plus C squared So I'll just write that up here so that you can see it, is greater than or equal to AB plus BC plus AC. So that was the part B result, okay? So just need to keep that in mind for part C. Again, here we use this result because A plus B plus C was 1. Also, we use this result because we know a relationship between this bit and that bit from part B, okay? Start off with this. Now, because we know that A squared plus B squared plus C squared from part B is greater than or equal to AB plus BC plus C squared, we therefore say that that's greater than or equal to, so we can say, well, A plus B plus C squared is greater than or equal to AB plus BC plus AC plus 2 lots of AB plus BC plus AC. Now we know that A plus B plus C is 1, so we've got that 1 squared is greater than or equal to, now we've got AB plus 2AB is 3AB, but we've also got 3BC because we've got 2BC and a BC, so we've got 3 lots of AB plus BC plus AC, okay, and therefore we can just divide by 3, so therefore we've got that AB plus BC plus AC, that 1/3 is greater than that, or you can just write it the other way around, AB plus BC plus AC is less than or equal to 1/3, okay? So that's part C, okay? Now in part D, the question is to state the condition for equality to hold. So state the condition, for the equality to hold. So in other words, what the question is asking, when will AB plus BC plus AC equal 1/3? And that will happen if, now if we look at the result A plus B plus C is 1, and the only way that that would happen for equality would be if A was 1/3, B is 1/3, and C is 1/3 is 1, then we could say, well, AB plus BC plus AC is 1/3, then equality would occur if, and only if, A is 1/3, B is 1/3, C is 1/3. So you'll get equality if A is 1/3, B is 1/3, and C is 1/3, because if we look at this, you'd have 1/3 times 1/3, which is which is 1/9, and here you'd have 1/3 times 1/3, and here you'd have 1/3 times 1/3, so that's 1/9 plus 1/9 plus 1/9, sorry, I was off the screen, is 3/9, which happens to be 1/3. So therefore the condition for equality to hold would be A equals B equals C, which are all equal to 1/3. And I suppose you can relate that back to here. If you've got, see, this and this is similar, this is just being divided by 3. So if 1/3 plus 1/3 plus 1/3 is 1, then if you divide these all by 3, then you'll get A over 3 plus B over 3 plus C over 3 is 1. So therefore you can deduce that each of these would be 1/3 using where you've got AB, BC and AC, okay? Here's an example from the 1984 HSC. Given that X, Y and Z are positive numbers, prove that part A, x squared plus y squared is greater than or equal to 2xy. That's fairly straightforward. And we're going to look at part B as well. Okay, now let's have a look at those. So our solutions, why don't you pause the video and attempt these, and then you can turn the video back on when you're done. So can you attempt question A and B, and then you can restart the video. Okay, solution for A. We'll start with x minus y squared is greater than or equal to 0. Therefore, x squared minus 2xy plus y squared is greater than or equal to 0. So x squared plus y squared is greater than or equal to 2xy. That's your part A. Now for part B, we need to show that that's greater than or equal to 0. Now we can just do this similar thing. So we've got equation 1. So from that we can say similarly using equation 1. So similarly using equation 1, we know that, again, we've got 3 terms here, so we're going to have to double up. Using equation 1, we've got that y squared plus z squared is greater than or equal to 2yz. That's equation 2. And we can pair up x squared with z squared is greater than or equal to 2xz. That's equation 3. We can double these, or we can add these all together. So doing equation 1 plus 2 plus 3, This is very similar to what we've just done, okay? We get 2x squared plus 2y squared plus 2z squared is greater than or equal to 2xy plus 2yz plus 2xz. Here we can just divide through by 2, same as what we just did, okay? So it's just a bit of practice for you. You will get that x squared plus y squared plus z squared is greater than or equal to xy plus yz plus xz, and then taking it all over to the left, we get the x squared plus y squared plus z squared minus xy minus yz minus xz. So minus xz is greater than or equal to 0. So that's parts A and B. That should all be fairly straightforward for you. Again, the hint here is because you're trying to prove this thing with 3 terms where the x squared, yz squared and z squared, you know you have to do doubling up of this x squared plus y squared is greater than or equal to 2xy. You've got to do it 3 times so that each of the terms is doubled, and then you'll divide through by 2. Now for part C, we'll do that over the page. And you can try it on your own and then restart the video. It says multiply both sides of the inequality in part B by x plus y plus z to obtain this. Now obviously you might want to take these over first before you do that, okay? Part C, you have to obtain this result or prove this result. Now from part B we had this, that was the second last step in part B. So multiplying, as they've said, both sides by x plus y plus z, we've got that x squared plus y squared plus z squared times x plus y plus z, and we want to multiply this right hand side also by the x plus y plus z. Okay, now I'll just do that quickly. Hopefully you've already done this. If you haven't, pause the video and just try and do it on your own, you know, cancel like terms, etc., and you should come up with that result. So we get x cubed plus x squared y plus x squared z plus y squared x plus y cubed plus y squared z plus z squared x plus z squared y plus z cubed, this is getting quite long, is greater than or equal to x squared y plus xy squared plus xyz plus xyz plus y squared z plus yz squared plus x squared z plus xyz plus plus xz squared. Hopefully I haven't made any mistakes there. Now let's just look for our like terms that we can cancel. Okay, I think that x cubed plus y cubed plus z cubed, there are none of those on the right hand side, so they will stay. Here's the x squared y, that can cancel, so that cancels with this one. X squared z, yes, there's one on each side there. Y squared x, one each there. Y squared z is there. Z squared x, that one. Z squared y, that's that one. So they all cancel. So therefore we've got that x cubed plus y cubed plus z cubed is greater than or equal to x, there's 1xyz, 2xyz, 3xyz. Okay, so that's part C proven. You know, fairly straightforward, not difficult, just some expansion there. And in part D, you have to prove or deduce from part C, or otherwise you have to deduce that x plus y plus z times x to the power of minus 1 plus y to the minus 1 plus z to the minus 1 is greater than or equal to 9. Okay, now using this result, it says deduce from part C or otherwise. What we're going to do, as I showed you in that first video, we're going to do replacements of variables. Now, if x cubed plus y cubed plus z cubed is greater than or equal to 3xyz, then if I want to come up with an expression for just x plus y plus z, because I'm going to need it here, that would be greater than or equal to 3 times the cubed root of x times the cubed root of y times the cubed root of z, which means that x plus y plus z is greater than or equal to 3 times the cubed root of all those, okay? Now, similarly, we're looking for an expression for x to the minus 1, y to the minus 1 plus z to the minus 1. Now, that is really just 1 on x plus 1 on y plus 1 on z. Now, again, we're going to replace each of those terms here. So we're going to replace the x with 1 on x, the y with 1 on y, and the z with 1 on z. So we can say, well, that, similarly, that is greater than or equal to 3 times the cubed root of 1 on x times 1 on y times 1 on z. Okay? Now, I'm not sure what numbering I'm up to. I think this was equation 4. I'll call this equation 5 and calling this equation 6. And what I was doing with equation 5 here, what we did was we replaced x cubed with an x, we replaced y cubed with a y, and we replaced the z cubed with a z from equation 4. And here we've basically replaced the x with the 1 on x, you know, the y with the 1 on y. That's what we did there, and the z was replaced with the 1 on z, okay? So that was what was done there. So replacing and replacing. That's how we came up with equations 5 and 6. So now we want to come up with an expression for x plus y plus z times that. So we've got x plus y plus z times 1 on x plus 1 on y plus 1 on z. So we're doing equation 5 times 6, okay? I'll just make some room there. So we're doing equations 5 times 6, okay? That is greater than or equal to 3 times 3 is 9. So it's 9 times the cubed root of x, y, z times the cubed root of 1 on x, y, z, okay? And now rewriting this, x plus y plus z, and this is really x to the minus 1 plus y to the minus 1 plus z to the minus 1. Well, that's greater than or equal to 9 times. Now, if we're doing the cubed root of a times b, it's the cubed root of a times b, all under the same cube root sign. So it'll be xyz times 1 over xyz. Now we know that that is 1. So we've got x plus y plus z times this is greater than or equal to 9 times the cubed root of 1, which is 9. So therefore that result is greater than or equal to 9. Okay, I'll just write it out again. All right. Okay, so therefore the result is